Welcome again. Today we will discuss organic reagents based on gold. So, as you can see, this gold is in here, it is in the same group with copper and it is in the 7th row element. So, first we will discuss basics about gold chemistry. So, organogold chemistry is the study of compounds containing gold carbon bonds. The dominant oxidant states for organogold compounds are one with coordination number 2 and a linear molecular geometry. So, gold 1 has linear geometry. On the other hand, gold 3 with coordination number 4 and a square planar molecular geometry. So, gold 3 has square planar geometry. The first organogold compound discovered was gold 1 carbide Au2C2, which was first prepared in 1900, and in aqueous solution without stabilizing ligands, gold 1 disproportionates to gold 3 and gold 0 spontaneously. So, gold 1 will disproportionate to gold 3 and gold 0 in aqueous solution. The diamagnetic character of both gold 1 and gold 3 conveniently allows the monitoring of catalysis reactions by NMR. So, this is very important. Gold 1 and gold 3 are diamagnetic. So, you can get their study by NMR. And gold is less expensive than platinum, rhodium, iridium. This is also very important. Though we think that gold is expensive, but it is less expensive than platinum, rhodium and iridium. Redox stability, the resistance toward oxidation or reduction eliminates the requirement for reprocessing. Chemoselectivity, tolerance to oxygen bearing functional group simplifies the wider synthetic routes and imparts step economy in the constant of target oriented synthesis. So, this is very important. The oxygen bearing, we will see oxygen bearing functional group it can tolerate. And reaction profile from simple starting material to products of significantly increased complexity. So, this is very important. We will see that gold catalyze many tandem reaction and you can get compounds of higher complexity. Miscellaneous, operationally safe, simple and practical to perform, tolerance to both oxygen, air stable and acidic protons, that is the moisture stable. This is also very important. This is air stable as well as the acidic condition you can use. So, first we will study activation of alkynes, because this is the major reactions of gold, and then we will discuss activation of alkenes and then we will discuss activation of alkenes. So, all have pi bonds. So, what does it mean? Pi bonds coordinate with gold. So, that is the major chemistry of gold, that the pi bonds will coordinate with gold and that will make an electrophilic species and then defined nucleophile can react to alkynes, allenes and alkyne. So, first we will discuss activation of alkynes, and here we will discuss nitrogen nucleophiles, hydroamination, then we will discuss Schmidt reaction, this is with azide. Then we will discuss oxygen nucleophiles, hydration we will discuss, hydroalkoxylation we will discuss, carboalkoxylation, then carbonyl oxygen, that is the CO group also participates. And sulfur nucleophiles, carbothioylation we will discuss, carbon nucleophiles also we will see, enolates and enol ethers. Then hydroarylation we will discuss, enine cycloisomerization 1,6 and 1,5 enines, en plus ine. So, double bond plus triple bond is present. Then we will discuss propargyl esters and we will see 1, 2 and 1, 3 migrations. So, general, what is the general mechanism for simple nucleophiles? So, the prototypical mechanism involves initial binding of gold to the pi system followed by a concerted attack of a nucleophilic species. So, whatever we told that gold will coordinate with the pi system and then a nucleophilic attack will happen, and so like this this is gold 1 or gold 3, then here it has an alkyne, and now the coordination. So, this is the coordination. Coordination of gold to the triple bond happens, and now a nucleophilic species will attack. So, this is the nucleophilic species is attacking to the gold, and this is very important, they are anti. So, nucleophile and gold will be in the anti orientation. So, that will be the selectivity also we will see, and after that, so it will give a pi eta 1 vinyl species. This species then undergoes proto-deoration to give the corresponding alkene. So, this is the one acidic proton has to come here. So, this can be thought that this nucleophile, if it is oxygen or nitrogen, then what happens? It can also with its lone pair, it make like this, and here a H plus comes. So, this plus R1 R2 gold. So, here this hydrogen comes, and now what will happen? This gold will eliminate. So, minus gold, then you get R1 nucleophile, R2 and hydrogen. Of course, a double bond is present here. So, this is the mechanism that the nucleophile attacks in the anti orientation with the gold, and after that proto-deoration happens. So, an acidic proton has to come and this gold eliminate. So, this is very important in the gold chemistry, that gold can add and can eliminate without disturbing. So, it can facilitate the reaction and then it can eliminate so easily. So, you do not need any oxidant, that is the fancy of the gold chemistry. So, we will see different reactions. First, we will see intra and intermolecular hydroamination, like this, a primary amine. So, this is primary amine and alkyne is here. Now, with NaAuCl4 5 mole percent, acetonite solvent 79 degrees centigrade 1 to 2 hours, and R1 can be terminal or internal alkyne, R2 is equal to hydrogen methyl alkyl. So, this can be substitution or hydrogen is possible, and then you get this intermediate. So, what is this? So, if you see the number 1, 2, 3, 4, 5, 6. So, this is 6 decyclization is happening, and as I told, the gold will be here. So, this if you draw the intermediate with the gold, then it will be like this. So, gold will be here because this is the nucleophile NH, NH is the nucleophile, gold will be here, and after proton from the solvent, this gold will eliminate and will give this enamine. So, this is enamine, and after tautomerization, so this is tautomerization, you get the imine. So, after tautomerization you get the imine, and this reaction is quite general, and you up to 7 examples and 64 to 92% yield. This was published in Heterocycles 1987. So, this is intramolecular, and now we will see intermolecular. So, in the intermolecular there is a separate alkyne, and here they have used aromatic amine. R1 can be alkyl aryl, R2 can be hydrogen alkyl. So, with terminal alkene also will work, and with pH3P AuCH3 0.01 to 0.5 mole percent, and H3P, this is another co-catalyst, H3P W2O40 0.05 to 1 mole percent, this is solvent free reaction 70 degree centigrade, you get this imine. Two imines can be possible, but the Markovnikov regioselectivity will happen. So, the addition will take place at the more substituted center, that we will see, and this product is obtained 28 to 99% yield. This was published in Organic Letters. So, we will see the mechanism now. So, this is the active catalyst, and now if it is terminal alkyne is there, then this coordination happens first, coordination, and now this amine can add to the gold first and will make a species like this, and now the addition will take place. So, as you can see, this addition takes place selectively where at the more substituted. So, amine adds to more substituted carbon atom, because that is the Markovnikov rule, because here the carbocationic character will generate at this carbon. So, amine reacts here and gold, actually gold can coordinate and gold ultimately comes here, and then after this proton the elimination of gold will happen. So, gold also is eliminating here, this is the active catalyst, and you get this imine product. So, this is very important, the imine formation from alkynes and amine, primary amine, you can with the gold you can generate the imine, and the amine addition takes place at the more substituted carbon atom. Intramolecular hydroamination, synthesis of indole also is possible, like here if you see this, this is aromatic group, this is the alkyne, this is internal alkyne, and this is the amine with NaCl Cl4 2H to 5 mole %, THF room temperature 2 hours, you get this indole. So, this is very important product, 2 substituted indole. Indole is formed in 87% yield. If you see the mechanism here also, the gold will coordinate to the triple bond, and now the addition will take place. So, this way addition will take place and gold will come of course here, and you get this intermediate. Gold. So, here you can see this is 1, 2, 3, 4, 5. So, this is 5 endo decyclization, and this process is very facile because indole, you know, this is aromatic. So, this process will be very facile. So, you get the indole after gold elimination. This is tertiary butyl, N-butyl, N-butyl. So, this way you can get easily indole products. Now, we will discuss synthesis of pyrrole via inter and intramolecular path. So, you can see here a carbonyl group is there, this is the enamine and a triple bond is present, and this carbonyl group does not participate, but this enamine participates. So, this nitrogen adds to this triple bond, and so 1, 2, 3, 4, 5. So, this is 5 exodic. 5 exodic cyclization happens and you get an aromatic product. So, this is aromatic. So, whenever aromatic product forms, this process should be very facile, and you can see it is quite substituted, 3 substituted pyrrole is formed, and ethanol solvent 75% yield. Now, this reaction you can also do with 1,3-diketone. So, this is 1,3-diketone, because if you mix 1,3-diketone and benzyl amine, then also you get this intermediate. So, this is the you do not have to preform this one, in situ we can generate this from mixing this 1,3-diketone and benzylamine under the same condition NaOCl4 2H2 5 mole %. Here just temperature you have to decrease to 40 degree centigrade 2 hours and you get 100% yield. So, this is very efficient reaction for this indole synthesis. Mechanism will be similar, that the gold will coordinate, and as I told that the gold and the N nucleophile will be in the trans orientation and that will give the methyl group here. So, this methyl is forming here actually. So, this carbon is going to a methyl group, and synthesis of amino indologens. Here also you can see this is pyridine carbaldehyde. Similar reaction, pyridine carbaldehyde, this is alpha amino ester and phenyl acetylene. You get this amino indologens. Similar reaction, and only 1 mole % NaOCl4 2H2 is enough to give this product. Here also solvent free condition can be used, and 60 degree centigrade you get very good yields. So, we will see the mechanism of this reaction. So, pyridine gold catalyzed 3 component coupling of pyridine 2 carboxyaldehyde, amine and alkyne occurred to afford NaR1R2 substituted propargylic pyridine 4 via Mannich-Gigner reaction. So, iminium is formed. So, this is the iminium. CH(R1R2) and you get iminium ion. So, this is the iminium ion in situ form, and then the triple bond ends here, and after the addition you get this 4. Coordination of this triple bond in alkyne 4 to the gold catalyst enhance the electrophilicity of the alkyne, and the subsequent nucleophilic attack of the nitrogen lone pair would produce the cation 5. So, this anti addition takes place. After that, this gets a positive charge and gold is here, R3 is here, and now a deprotonation will happen, which undergoes deprotonation followed by demetallation to afford indologens. So, this proton will eliminate to generate this species, and now again an H plus. So, this is the removal of gold, always like this. So, if you have a proton, then the gold will eliminate and you get this hydrogen here, and these indologens are obtained in this way, very efficient way you can get indologens. This was published in Organic Letters 2007. Now, we will see intramolecular acetylenic Schmid reaction. So, in the Schmid reaction azides are used. So, you can see this azide is there and alkyne is present, and similarly here also you get pyrrole. So, pyrroles you get here also substitute pyrroles and defined functional groups. R1 can be hydrogen, alkyl, cyclic, R2 can be also like this or cyclic, R3 is equal to alkene and furanyl cyclopropyl. You get 41 to 93% yield under this condition DPPM. So, this is the structure of DPPM. Diphenyl phosphonomethane, and we will see the mechanism of this reaction now. This reaction is quite efficient with DPPM Au2Cl2 2.5 mole % and AgSbF6 5 mole %, dichloromethane 40 degree centigrade, you can get good yields. So, what could be the mechanism? As always, the triple bond will coordinate with the gold, and now this N minus will attack here. So, this is also 5 endo-dig. So, 5 endo-dig cyclization will happen, and so this is the newly, this red is the newly generated bond, and R3 is, and now nitrogen eliminate and this gold will this gold lone pair will circulate like this with the elimination of nitrogen. So, this process will be very fast because nitrogen gas will eliminate and you get this intermediate. A mechanistic hypothesis involving gold 1 induced activation of the alkyne toward addition by the proximal nitrogen of the azide, subsequent loss of dinitrogen produces cationic intermediate which is stabilized by electron donation from gold. A formal 1,2 shift regenerates the cationic gold 1 catalyst and produces a 2H pyrrole that tautomerize to the 1H pyrrole product. So, 1,2 hydrogen shift will happen. So, this one will shift here. So, this is 1,2 hydride shift. Hydride shift and here carbocation will generate here and then this double bond will generate, gold will eliminate. So, that is the facile that the gold can eliminate so easily. After that gold will eliminate and you get this first 2H pyrrole because this is not aromatic and then the tautomerization. So, this way the tautomerization will happen and you get the aromatic. So, this is aromatic. This was published in JACS 2005 127 11260. Now, we will see intermolecular hydration and hydroalkoxylation. This is also important reaction because you can get ketal. So, here a ketal is formed and of course, this 2 oxygen coming from the alcohol and if you see this triple bond is reacting here and this carbon is actually here this methyl group and this double bond of course did not participate in this cyclization and with gold chloride 2 mole percent in methanol room temperature 30 minutes you get 99% yield of this product. So, what could be the mechanism of this reaction? A plausible mechanism of the gold 1 or gold 3 catalyzed cycloisomerization of bis homoproparylic diols. So, this is bis homoproparylic diol. So, this is 1, 2, 3. So, this is bis homoproparylic diols. The reaction may be initiated by the formation of the pi alkynyl complex A through the complexation of the unsaturated tryptophan bond to the gold catalyst. So, this could be the intermediate as always the triple bond coordinates with the gold and here also this alcohol can be activated by the gold. The coordination of the triple bond therefore enhance the electrophilicity of the alkyne as usually advocate for metal catalyzed reaction of alkynes. The addition of one alcohol may be favored by an intermolecular complexation of the OH group to the gold catalyst. The enol vinyl gold intermediate B then be protonolized. So, after the addition, so here you can see also 1, 2, 3, 4, 5 exo dig cyclization will happen and this intermediate will form and which then undergoes another intermolecular addition of the remaining alcohol leading to the cyclic ketal 2A. So, after this you can think that this will form RO like this, but this will be equilibrium with the oxonium because if some acid is there then and this alcohol will add to the oxonium ion to generate the ketal. So, this is very important. If homoproparylic diol is there and then the cyclic ketal formation can be done with simple gold catalyst. Gold will activate the alkyne as well as the one alcohol and then the 5-exo dig cyclization first will happen and then an oxonium of course will generate so that further the another alcohol will add to generate the ketal. This was published in JACS 2005. Now, we will see that more alcohols reaction. Here you can see a double bond. Earlier we have seen that double bond did not participate, and here double bond has participated, and double bond we know it can participate via Prince reaction, because double bond as nucleophile, then there is a possibility of Prince reaction. That is what is happening here, and this is another external nucleophile alcohol, gold chloride 2 mole percent, R2OH 60 to 85 degree centigrade, 12 hours you get this. So, R2 is here and this oxygen is here, and of course, this methyl coming from this carbon, and R1 can be methyl allyl isopropyl, X can be oxygen CH2 here, and R2 can be methyl ethyl propyl, defined alcohols, and 5 examples 88 to 96% yield. So, what could be the mechanism of this reaction? So, first this addition to the alkyne will happen. So, 1, 2, 3, 4, 5, 6. So, this will be 6 exodig. So, first 6 exodig will give you this intermediate after elimination of gold. So, now the second reaction is the Prince reaction. So, this with proton source, this oxonium ion will generate, as we have seen earlier also, this enol ether will be protonated to give this oxonium ion, and now this alcohol attacks to the double bond like Prince type cyclization you get here, and this carbon adds to here, so that you get a bicyclic compound. Now, you can see 3 component reaction. So, this is very important. This was intramolecular, this is intermolecular. Intermolecular reaction. So, an alcohol is refined, an alkyne is present, and another alcohol. This alcohol is used for the Prince. So, here after this if you mix them, then you get this. So, this is tetrahydrofuran. Tetrahydrofuran with cyclopropyl as usual was there earlier. So, it did not break. So, here what happens in the mechanism? So, here at first this OH will react here, and this OH will add in the Markovnikov fashion. So, this is following Markovnikov rule. As to the more substituted carbon of the alkyne, that is containing R2, and now this kind of transition state has been drawn to explain the desired stereochemistry. As you can see here, this OR3 group and this methyl groups are in the opposite phase. So, this kind of geometry it will orient, the alcohol will come like this and your methyl will be down. So, alcohol attack will take place from the top phase to generate this one, and the methyl will be down and R2 will be up, so that you get this. So, this is the newly generated carbon carbon bond here, because R3 attacks here, then this carbon attacks to here and you get a methyl group. So, this cyclopropyl containing tetrahydrofuran are obtained in 62 to 93% yield, and R1 R2 can be aryl, R3 can be alkyl. So, generally alcohol like ethanol, methanol, propanol can be added. Now, if you have an epoxide, so this is an epoxide. So, with epoxide and alkyne, so if you add alcohol, so what we know that alcohol can open an epoxide, nucleophilic opening of epoxide with alcohol as well as water can be possible, and you get after opening of epoxide you get this OH and OR here. Now, this OH can do the cyclization with the gold, and here of course the 6 exodig will happen, because you get a 6 member ring here. And for the condition A, you have to use pH3 gold chloride AgSb F6 5 mole percent ROH paratoluene sulfonic acid room temperature. So, acid is there, and with acid condition you can get this. So, oxonium ion will form here. After gold eliminates, you get similarly this So, this oxonium ion will generate. Now, the OR will attack. So, alcohol will attack, and so that you can get this kind of stereochemistry. It is from the top phase and this is down phase, and this product is obtained 44 to 80% yields with 9 examples. Now, for water you have to use similar condition, PH3P gold chloride AgS SbF6 5 mole percent water dichloroethane room temperature. Since water is there, water also this OH also will participate. So, that we will see now. See here 2 OH is there. So, this is the newly OH from the water. So, water opens the epoxide and always the attack taking place for the less substituted carbon, and you get this secondary alcohol OH again like this coordinates. And now, earlier what happened, the external ROH was attacking the oxonium ion, here this OH will attack to the oxonium ion and you get this bicyclic ketal. So, this is bicyclic ketal. This is formed in 38 to 70% yields with 6 examples. Now, we will discuss intramolecular carboalkoxylation. So, here if you see this ether is present here, of course, this is chiral, and here a triple bond is present. There are two things is happening, two important things. One, this methoxy group is transferred here, and another things the inversion happens. So, R1 was earlier up, now R1 is down. So, here inversion. And here defined groups can be incorporated. R1 can be vinyl aryl cinnamoyl, R2 can be alkyl aryl CO2Me, X, Y can be hydrogen CF3OMe and 41 to 99% yield. And this is the catalyst PCF3C6H4PeUCl 2 mole percent, HgBF4 here 2 mole percent, 5 angstrom molecular shift, dichloromethane room temperature. So, what could be the mechanism for this reaction? Because the methoxy group has transferred. So, what does it mean? It means the methoxy group has to coordinate to the alkyne and then that bond has to break. So, that is why that is how the methoxy can transfer. So, what will happen? A gold promoted intramolecular nucleophilic addition of the benzylic ether generates cationic intermediate 10. So, this is first formed because methoxy attacks to alkyne, of course, gold activated alkyne, and you get this, the trans LAU and O methoxy are in the trans fashion. Now, ionization, there is a positive charge with oxygen now. Ionization of the CO proceeds through a transition state 11 that maximizes overlap of the forming carbocation with the aromatic pi system and avoids interaction of the benzylic substituent R1 with the forming enol ether. So, after this methoxy transfer to the double bond and here a carbocation will form, and this carbocation will stay in such a way that this R dash and methoxy will be in the further, will stay further, so that minimum interaction will happen. This pathway allows for the center chirality of the CO bond to be retained in the axial chirality of the carbocation intermediate 12. So, here this axial chirality will stay of this carbocation, because it can stay in a particular orientation. So, this is the carbocation and this is 13. So, intramolecular addition of the vinyl gold moiety to the carbocation via transition 13 transfers the axial chirality to the CC bonds center chirality of the product kindine with overall inversion of the center. And now, this will attack here, this carbon with having the gold will attack here, and after gold elimination you get this indene. So, here this R dash is down, so that minimum interaction with this methoxy group and R dash will be there, and ultimately you get an inversion. So, this is very important process that the methoxy group transferred as well as the inversion of the chiral center, and this was published in JACS 2006. So far we have discussed the oxygen as the nucleophile. Now we will see carbonyl oxygen. So this is also possible, carbonyl oxygen as nucleophile. Suppose if you see here a carbamate moiety is there. So this is carbamate and a triple bond is present and you get this one. So this is addition is happening here. If you see 1, 2, 3, 4, 1, 2, 3, 4, 5. So this is 5 or 6 depending on A. So this is the exodic cyclization, 5 or 6 exodic cyclization which PH3P AuCl Ag SbF6 5 mole percent dichloromethane room temperature, you get this cyclic carbamate. So these are cyclic carbamate and N can be 1, 2, R1 can be hydrogen, that is the terminal alkyne, methyl, pH, CO2, R2 can be hydrogen, alkyl aryl, and you get 69 to 95% yield. So what could be the mechanism? The mechanism is like this. So this carbonyl adds to here and join the exocyclic olefin, and this gold will eliminate by a proton, and so the proton comes here, and this also will eliminate. So you get a carbonyl here. So this O tertiary butyl will eliminate. So you get a carbonyl. This was published in JOC 2006. Another reaction, if you have a triple bond and a diketone motif, of course you have to add additional alcohol with gold chloride 2 mole percent dichloromethane, you get this 5-member ring is formed, and as you can see red are newly generated bonds. So there are 2 carbon oxygen bonds are formed, and R1 can be alkyl aryl, R2 can be alkyl alkynyl, R3 is equal to methyl ethyl phenyl tertiary butyl isopropyl allyl, and the products are formed in 42 to 88% yield. So what could be the mechanism? Here also the triple bond is activated by gold 3 here, and now this alcohol will attack to this carbonyl specially, so that there is a possibility of the 5-member ring. So this alcohol reacts here, now this oxygen attacks to here in the 5 endo-dig. So 5 endo-dig cyclization happens, and gold of course will be here, and after elimination of gold you get this compound, and the products are formed in 42 to 88% yield. This was published in Organic Letter 2006. There is another reaction. So here this is very important. There is 2 alkyne, one molecule has an aldehyde group. So this is a aromatic group attached to the alkyne, and externally another alkyne which is as a nucleophile. So this is actually nucleophile. So gold does not bind with it is just nucleophile. Gold binds here, and with trimethyl phosphine AuCl 5 mole percent, diisopropyl ethylamine 20 mole percent, water toluene 1:1 to 5:1, 60 to 90 degree centigrade, one day you get this product. So 6-member ring is formed, and here also 6 endocyclization happened, 6 endo-dig happened, and this is the external alkyne, and this red are 2 newly generated bonds, one is carbon oxygen, another CC bond, and these products are formed in good yield 16 to 89% yield. R1 can be aryl alkene, R2 can be aryl alkene, and this is the intermediate. So this aldehyde will attack here, and of course the oxonium will generate here, and that will react with this alkyne. So the oxygen become single bond now, and this gold will eliminate with H plus, you get a H here, and the desired products are obtained in very good yield. So this was published in Organic Letters 2006. Another reaction, if you see this one, this is a cyclopropyl group is present, a carbonyl group is there, a alkyne group is present, and methanol is there externally. So methanol is a nucleophile, and with PH3P AuO triplet 1 mole percent methanol dichloromethane room temperature, you get this. So, this is furan. Furan is formed with R1 substituent, R2 substituent, and here methoxy group is present. And what could be the mechanism? So, this carbonyl coordinates here. So, this is also 5 endodig. So, 5 endodig cyclation gives this oxygen and gold are on the opposite side. And now, this cyclopropyl group, because the oxonium will generate after the carbonyl attacks to the triple bond. So, what happens? This becomes, earlier we have seen here also we have seen alcohol came, here alkyne came, and here the cyclopropyl group is present. So, the cyclopropyl open because this is with the molecule itself. So, because this is hindered, so the cyclopropyl group open and it will react here, so that a carbocation will generate here, and that one will react with methanol to generate give this product. And R1 can be hydrogen, alkyl, vinyl, aryl, TMS, R2 can be alkyl, R3 can be alkyl, aryl, alkoxy. The products are obtained 35 to 96% yield, and this was published in Angiochemy 2006. Now, we will see rearrangement of alkynyl sulfoxides. So, you can see there is a sulfoxide and alkyne motif. And now, with PH3P, AuCl, AgA, SbF6, 5 mole percent, or imidazole, MEs, AuCl, that is the heterocyclic carbene, and AgA, SbF6, 5 mole percent, dichloromethane room temperature to reflux, you can get the 7-member ring or this 6-membered. So, when R1 is equal to ethyl, so this is the R1. If R1 is equal to ethyl or alkyl, then you get the 6-membered. And if R1 is equal to hydrogen or electron donating group EWG, then you get this 7-membered ring. So, what could be the mechanism? So, there is certain factors that is governing the formation of 6 or 7-member ring. So, that we will see now. So, if R is equal to hydrogen, here you can see R is equal to hydrogen, then this oxygen is attacking here. So, 5 exodig is happening here, and you get this 5-member ring. And now, this double bond will go here, double bond will make a carbonyl, and this will form. So, this is the mechanism that the coordination of catalytic gold 1 to the alkyne induces nucleophilic addition of the sulfoxide oxygen. When the alkyne is terminal or substituted with an electron withdrawing group, 5-exodig cyclization of the nucleophile onto the terminal carbon of the alkyne is favored, yielding intermediate 23. So, this is formed. This is 5-exodig cyclization. So, this is Friedel-Crafts reaction. Because pH you can draw like this, SPH, and now this carbon will react to here and you get this. So, this R is equal to here hydrogen, that is why R was not shown here. So, this is actually R should be here, and you get a 7-member ring. On the other hand, if R is equal to ethyl, so then what will happen? Then this will happen that the 6 endodig. So, earlier was 5-exodig. So, on the other hand, when the alkyne is substituted with an alkyl group, 25 is generated by a 6 endodig cyclization. After cyclization, gold 1 assisted sulfide release produces gold carbenoid intermediate 24 or 26. So, after that, similarly the sulfur oxygen bond will cleave and you get this. And now again you have a, if you draw the SPH, you can draw like this. So, the Friedel-Crafts reaction will happen at this carbon. So, this is Friedel-Crafts reaction, and here in this case this ketone is outside. So, here and you get phenyl carb products. So, 6 member ring is formed. Finally, carbonyls 24 and 26 undergoes intramolecular phenyl carb alkylation to produce the observed products and liberate the cationic gold catalyst. Depending on the substituent on the alkyne, either 6 member or 7 member ring can be formed. So, for 6 membered you have to use alkyl group, and 7 membered you can use terminal hydrogen or electron withdrawing groups, so that the exocyclization will happen, because then the electron pooling will be there if R is equal to hydrogen, because that will stabilize this one, the negative charge which is happening at the carbon connected to the gold, because with electron withdrawing group that 5-exo decyclization will be facile. This was published in JACS 2007. Now, we will see enolates and enol ethers as nucleophile. You can see this is beta keto ester and with the alkyne, and this is the catalyst PH3P AuCl AgO triplet 1 to 5 mole percent dichloromethane room temperature. You can get this exo endo products. So, this is exo, this is endo. In exo, like earlier we have seen, the exo decyclization happens. So, this is 5-exo dig, 5-exo dig, and this is 5-endo dig. And these are the journals which publish this work. So, we will see the mechanism now. So, depending on the n is equal to 3, we will see n is equal to 3, then the R is important. So, mechanism involving nucleophilic addition of an enol to a gold alkyne complex. Based on this mechanistic hypothesis, one of the potential explanation for the lack of reactivity of non-terminal alkynes in the gold catalyzed 5-exo decyclization. So, non-terminal alkyne will not react in the 5-exo decyclization. Is that the placement of the catalyst near an alkyl substituted carbon atom is sterically unfavorable. So, after 5 decyclization, this intermediate will form, because this will stay as an enol and this OH will interact with R, and that is why this 5-exo decyclization only will happen when R is equal to hydrogen. And after this 5-exo decyclization, you get this. As you can see, nucleophile is here added and gold is opposite side, so that this olefin will be cis to this CO2 group after elimination of gold. Now, on the other hand, if n is equal to 2, then you can get 5-endo decyclization. And here in the transition state for the endocyclic reaction, the gold center is located near an alkyl substituted carbon atom without inhibiting the cyclization. So, in the 5-endo dig case, there is no problem, because the gold is coordinated to the other space and OH is here. So, there is not any steric interaction. So, here the non-terminal alkynes can be incorporated for this 5-endo decyclization, then you get this, and after elimination of gold you get this. So, cyclopentane is from here, and here the exocyclic bond is there, exocyclic double bond. If depending on the cyclization is happening, that the 5-exo decyclization, if you have a R group, then this R group, then it fails the steric interaction. So, only with terminal alkynes you get the 5-exo decyclization. But 5-endo decyclization, it can work both with terminal as well as non-terminal alkynes. Now, we will discuss hydroarylation. So, you can see this is mesitylene, and with phenyl acetylene you can get this kind of product. Of course, the attack takes place the more substituted. So, attack at the more substituted carbon atom, and you can get this with AuCl3 1.5 mole percent, AgSbF6 3 mole percent, you get this product, and 9 to 100% yield with acetonitrile 50 degree centigrade. On the other hand, if you are an electron deficient is there. So, this is ethyl propargylate, and with pH AuCl 1 more percent, AgSbF6 1 more percent, you get this. So, what does it mean? Because gold is here, so that's why the intermediate gold was here, that is why this kind of geometry is formed. And here this is also following the Markovnikov addition, because here the most substitute is happening, but here the electron, that is the electron rich carbon atom, will have the A star group, because the A star is electron withdrawing. So, this carbon will be electron negative, and that will be stabilized by CO2 group, and this also obtained in 0 to 98% yields with 8 examples. So, this is the mechanism that the phenyl acetylene coordinates with the gold, and then the aryl Fidelkov reaction. So, this is Fidelkov reaction happens, and you get this. The more substituted carbon atom reacts, because the gold for the pH case, this will be the less substituted. So, here the negative charge will be stabilized, and after protonation you can get this, gold is eliminated, and in this case ethyl propargylate you get this coordination, and here the Fidelkov reaction will happen to this carbon, because the negative charge of course will be stabilized by CO2 ET group, because here a negative charge is present, that is stabilized by CO2 ET group, and after acidic workup you get this. So, this is the Z olefin, because the Ar and gold are always opposite. So, nucleophile and gold are always opposite, and that determines the stereoselectivity of the olefin. So, here Z olefin is formed. This was published in European JOC 2003. Now, we will discuss intramolecular hydroarylation 3+2 cycloaddition as a Claisen rearrangement. So, you can see here a triple bond is present, triple bond, double bond, and N tosyl group is there, and with this one PCF3, PH3, PEAU, NTF2, 2 mole percent dichloromethane room temperature, you get this. So, this is of course pyrrole, and the substitutions are there, and R1 can be methyl pH, R2 can be hydrogen methyl, R3 can be hydrogen alkyl aryl, R4 can be, so this is aryl, R4 can be hydrogen methyl, and these products are from 70 to 97% yield, 11 examples. So, what could be the mechanism? So, as you know, the N tosyl is a nucleophile here. So, N tosyl will react first here. So, this is 5-exodig. So, for terminal case you can get the 5-exodig, and 5-exodig forms, and N tosyl, this carbon nitrogen bond and gold are in the opposite side. And after that, as a Claisen rearrangement is there, because you can see this is nicely fitted 1, 2, 3, 1, 2, 3. So, 3 atoms are present. So, that is suitable for the rearrangement. This is the Ajak Claisen rearrangement, 3 sigmatopic rearrangement. So, this is 3 sigmatropic rearrangement, and after the rearrangement you get the iminium ion, and the double bond is formed here, and R3 R4 is here, quaternary center newly generated. And what will happen now? A hydrogen will be eliminated from here. So, you get like this, the aromatization, and after removal of gold, because gold can. Now, we will see ring enlargement reactions. So, here is a epoxide is there, the epoxide can be opened. So, earlier we have seen the epoxide can be opened with external alcohol, but here the epoxide is opening itself, because the triple bond is activated by the gold 3 mole percent. So, it is activated, and that is why it is neighboring. So, what will happen? This oxygen of course will attack, and you get a furan. So, this hydroxy group is not participating, here you get the furan. So, what could be the mechanism? So, this could be the mechanism after opening. So, this opens like this oxygen attacks here. So, like this you get this carbocation forms here, and here is the gold. So, this is the newly generated bond, oxygen carbon bond is formed. This also newly generated carbon gold. And now, like earlier, the aromatization will take place like this, the H plus will eliminate and H plus will add here. This is the hydrogen is coming from the H plus. After gold elimination, you get this product in 84% yield. This was published in Advanced Synthesis Catalysis 2004. This is another opening. You have a cyclopropyl group and ether and an alkyne is here. So, what will happen? Here the cyclopropyl opening is happening. Propyl opening. Because whenever cyclopropyl is connected to ether, this is pulling electron. So, this will react and that is what is happening. So, this is reacting here. Here interestingly depending on the N, so N can be 1 is cyclopropyl, N is 2 is equal to cyclobutyl, you can get this kind of ring and the carbonyl group is formed here, that is the newly generated from this ether and this is the newly generated bond is formed and gold is here and now after elimination you get this exocyclic olefin and the carbonate and this is the catalyst PCF366H43P gold AgSbF6 0.5 to 5 mole percent dichloromethane room temperature you can get this product. So, this is cyclobutanone with exocyclic double bond. This was published in JACS 2005. Now, we will discuss cycloisomerization of 1,5-enine. You can see here a double bond is present, here a triple bond and here an ester with gold 3 chloride 5 mole percent, various conditions you get this bicyclic compound. So, one more cycle has been formed and this product is formed in 64 to 86% yield. So, what could be the mechanism? So, here also this will attack first to the terminal double bond and here the 6 endo dig will happen. 6 endo dig will give this intermediate, oxonium ion is here and now if you see there will be many reactions because this oxonium ion is pulling the electrons. So, all electrons will go to that direction. So, this is negative charge, this will first attack here, then the double bond will migrate here and this will open and ultimately AR is here. So, if you see this is the AR and now this new bond formed and of course, gold will eliminate keeping the double bond here and this becomes COO. So, OCOR will form. This was published in JACS 2005. If you have a OTS group that also can participate. So, we will see now here with a double bond and a triple bond with PH3PAUCl AgSbF6 5 mole percent isopropanol 1.1 equivalent dichloromethane room temperature you get this cyclopentene. So, this could be the mechanism. So, double bond reacts here. So, 6 endo dig. Then you get a carbocation here and now this carbocation because this gas is there. So, it will push the electrons. So, this bond will cleaved, this bond will cleaved and this will ultimately go to aldehyde having a quaternary center. So, this is the newly bond formed and gold will eliminate to give the double bond here. This was published in JACS 2006. Now, if you have a alcohol, a double bond, a triple bond, this is pH, then also the reaction will happen with gold chloride 5 mole percent acetonitrile room temperature you get this. So, what happens here also similarly this will attack here. So, 1, 2, 3, 4, 5, 6 endo dig. 6 endo dig cyclation will give a carbocation and that carbocation. So, this carbocation will form before this carbocation that then the alcohol reacts and if it is down then it is down phase attack. So, this is the scene syn orientation, because if it is down, then it will attack from the down phase to give this compound in this geometry, and you can get up to 89% yield. Gold catalyzed addition of carbonucleophile to Pubertyl carboxylate also is possible, like this OCOR3 with nucleophile. You can get 1,2 addition or 1,4 addition via 1,2 acyl migration. On the other hand, 1,3 acyl migration is possible also with nucleophile gold. You can get this. So, what could be the mechanism here? So, pubertylic ester 1 undergo 1,2 or 1,3 acyl migration with gold 1 complexes via intermediates 2 to form highly reactive unsaturated gold 1 carbene 3 or gold 1 coordinated allenes 4 respectively. So, either this 1,2 acyl migration, if you see the migration is happening here at this center. So, this has opened, or 1,3, for 1,3 gets you can get this 4 which isomerizes to 4 dash actually. Usually depicted in similar as gold coordinate allenes 4 dash and will deliver 7. So, this will give 7 after nucleophile adds to this. So, nucleophile add here. So, nucleophile add here and then you get this compound. And now, this carbene 3 formed by 1,2 acyl migration of 1 react with nucleophiles to provide 5, 6. So, here either 1,2 addition can be possible, the nucleophile add here. On the other hand, nucleophile can attack here and then the double bond will migrate. So, 1,2 4 addition also possible, and when R2 is equal to hydrogen, that means this is not sterically hindered because one side of the double bond is open, and when both are substituted, then this 1,2 addition is facile. Now, we will discuss activation of allenes, nitrogen nucleophiles, hydroamination, oxygen nucleophiles, hydroalkoxylation, carbonyl oxygen, carbonucleophiles, hydroarylation of alkenes, intramolecular enantioselective selective hydroamination. So, this is NaCBA, this is chiral allene with this gold catalyst, silver triplet, you get this product in 74% E. This is the mechanism. Similar like alkyne, you can also here activate the allene and you can get this intermediate, and after elimination of gold you can get the double bond. Now, with chiral catalyst also you can get, so this is the biphosphine catalyst with AR this, you can get the product up to 81% E in 97% yield. This was published in Organic Letters 2007. Now, intramolecular version is there, intramolecular hydroalkoxylation is possible here, allene OH is there, you can get this 6-member ring, and this could be the mechanism that the allene first coordinates with the gold and OH will attack, so that 6 endocyclization happening to get this one, and after elimination of gold you get this. So, gold catalyst to the terminal double bond of the allene A gives rise to the formation of the intermediate B, which upon nucleophilic attack of the oxygen is transferred to the sigma gold complex C. Proto demetallation of the latter provides the heterocyclic product D and releases the gold catalyst into the catalytic cycle. This was published in Organic Letters. And 5-member ring can be also formed. Here you can see this different groups can be tolerated, you can get the products in good to moderate yields. This was published in Organic Letters 2001. Now, we will discuss this one. If you have a thiol, then also this cyclization will happen, and you can see the chiral product is formed with 88% yield greater than 99:1 DR. So, here also the mechanism will be like similar coordinates of the Lewis acid carbophilic gold catalyst to the terminal allenic double bond intermediate is required for an intramolecular nucleophilic attack via SNN2 type transition state to afford the Zwitter ionic species C. So, this is formed after attack, which upon proto demetallation is transformed into the heterocyclic product with complete axis to center chirality transfer. So, this is formed, and this is very important, the chirality is transferred to the product, as you can see. and this was published in Anglo and the Chemi International edition 2006. Now, we will see another reaction, Metala-Nazarov reaction. If a double bond and alene, so this is double bond and alene is present, then you can get this cyclopentadiene. So, this could be the mechanism that the gold activates the alkene, and then this double bond attacks to the alene, you get this carbocation over 5 carbon atoms, and that is the mechanism for Nazarov, Metala-Nazarov reaction happens. This is the newly generated CC bond, and after gold elimination and 1 to hydrogen shift. So, this hydrogen shifts to here, and you can get this compound. This was published in Anglo Chemi 2007. Last we will see activation of alkenes, nitrogen nucleophiles, hydroamination, 19 transfer, oxygen nucleophiles, hydroalkylation, carbon electrophiles, enolate. So, this is the hydroamination, sulfonamide is present, you can get this product in 88 to 100% yield, and you can see this one is present, then also is possible. This is the newly generated bond is formed. So, this is the hydroamination. This was published in Organic Letters 2006. And now we will discuss domino ring opening, ring closing, hydroamination. So, here you can see this double bond is present with tosylamine, toluene, 85 degree centigrade you can get this pyrrolidine. So, this is pyrrolidine are formed in 34 to 76% yield. And this is the mechanism, because of course, the cyclopropyl group has been opened. So, this is the ring opening cycle, and then so first this activation happens, the N tosyl groups attacks like this, and you get this of course. After this opening, the hydrogen goes here and N tosyl here, then it will coordinate with the gold again like this way, and the cyclization will happen to give this. So, first ring opening followed by ring closing cycle, you can get this product. This was published in Organic Letter 2006. Nitrogen transfer reaction, if you have a alkenes, then the azide, then the aziridine can be formed like this, stereochemistry, trans. So, the double bond geometry will be remain intact, like here it is 80% trans, here also this formed X only, here this. So, this are published in Anglo Chemi, and we will see the mechanism. So, this is mechanism with copper, I think similar mechanism with gold also, PHIO sulfonamide, you get this one. So, what could be the mechanism here? So, with PHIO RSO2 NH, this is from the nitrogen plus and double bond I, and that changes with metal, PHI elimination with metal. So, this is gold also, this will happen, gold 3, and you can get this one in double bond Cu, and that reacts with the olefin. So, that the transfer happens, that is the like cyclopropanation, this is the aziridination. PHIO mediated aziridination occurred even in the presence of water. The metal catalyzed degradation of iminoiodine leads to iodobenzene and nitrenoid 13 and the starting sulfonamide. This was published in JOC. So, catalytic asymmetric aldehyde reaction is also possible with gold. You can see this reacts here and this cyclizes here. You can get this kind of compound with good yield, and E chiral ligand, if it is there, you can get E also. So, this is the chiral ligand, ferrocene based ligand, and you can get this kind of transition state. The aldehyde is coordinated with gold, also this cyano group is coordinated with gold, and this also is making the enolate tertiary amine. This was published in 2 journals, JACS and JOC. So, today we have seen different gold catalyzed cyclization reaction. First we have seen the alkyne activation, and different kind of alkynes can be incorporated in a substrate and with a alkene. So, that you can get defined product. sometimes aromatization, and the gold elimination is very facile, we have seen, and the nucleophile and the gold will be in the trans orientation, that will also fix the geometry of the newly generated double bond. And then we have seen the gold can activate alene also, and different kind of cyclization we have seen, the alene and the double bond. And then we have seen the alkene activation. Lastly, in the alkene activation we have seen the cyclopropyl group, there it can give the first the ring opening and then the ring closing cyclization with sulfonamide. And lastly, we have seen the aziridine formation with a double bond. So, that also we have seen the iodoxybenzene and sulfonamide, the active nitrosamine intermediate will form, that will attack to the olefin and give the aziridine. Thank you.